There we go, finishing up 5.6. Hopefully we can finish this. You may remember when we did problems like this, it was basically our horizontal asymptote problems. And so you could probably recall my very lame Bobo-Botno eats DC rules. As long as you're doing your the limit as x goes to infinity, and you can see that the exponents are the same. If you divide your leading coefficients, then this horizontal asymptote would be at -4/3. Now the calculus that we did the limit for, if you recall, what we did is the limit as x approaches infinity and divide every piece by the denominator's highest exponent. And after we simplified, this cancels, one of these cancels, and if we did the individual limit that approaches 0, this individual limit approaches 0, these cancel, and you actually see the -4/3. But we can also use L'Hopital's rule, and again, the way we're doing L'Hopital's rule is based off the fact that if we plugged in, I know it seems weird, the direct substitution of plugging in infinity, we'd have an infinity minus infinity, but this infinity is actually larger. Again, you don't want to write equals, you just want to write the arrows. You technically have negative infinity down here, but it doesn't actually matter. As long as the top and bottom are differentiable, which you don't have to write down, at least in the past they have not required this, but in case they do in the future, I'm making that distinction. That L'Hopital's rule applies. And if we did L'Hopital's rule, it's a derivative of the top as x approaches infinity of, it would be 8x minus 5 over -6x. Uh-oh, we have another infinity over negative infinity. But that's okay, because we can just do the derivative of top and bottom again. And so we get 8 over -6. Well, as we look at that, there's no direct substitution to plug in, and we can just reduce that to be -4/3. Exactly what we learned before. So as we get into more difficult problems, as we look at this one, we could still do L'Hopital's rule, but I do want to point out that if it's bigger on bottom, degree is bigger on bottom, the answer should be y equals 0. And it still applies because if we did L'Hopital's rule, again, I'm just going to write infinity over infinity. And I'm not trying to go too fast, but I want to make this video somewhat short. Derivative of the top, derivative of the bottom. Still infinity over infinity. So do L'Hopital's again. And we have 10 over 18x minus 4. Well, now what we have, still going to put it, is 10 over infinity. And as we get infinitely large, as we get larger and larger numbers in the denominator, that's telling us that this function is getting closer and closer to 0. I always like to use the analogy, like, imagine that we had $10 to give to one person. Okay, well, that one person would get $10. If we had $10 to give to 10 people, each person would get $1. If we have $10 to give to 100 people, everybody would get, what, 10 cents? And the more people we get, infinite number of people, we're getting closer and closer to people getting a fraction of a penny. That's how I learned it. That's how it made sense to me. But it follows from our Bobo-Botno eats DC rules. So as we get into more problems like this, and by the way, it's definitely helpful to know the graphs. Like if you were to ask to graph natural log of x, because when you plug in infinity, it is getting infinitely large, just very slowly. It is going infinitely up. Same thing with this graph, same thing with exponential functions, although that one's pretty obvious that exponential functions are going infinitely up. Please don't forget, though, that e is not a variable. E is a number. Anyway, so as we do this, we do have infinity over infinity. They're differentiable functions on this domain, all positives. So the fact that we have differentiable and infinity over infinity implies, maybe put like an and in there, implies that we have L'Hopital's rule. So then we can do the derivative of the top, which would be 1 over 2x, times the derivative of 2x, which would be 2. And in the bottom, you bring that 1/2 in front. So a half of 2 is 1, x to the negative 1/2 power. And might actually be worth your while to rewrite that. As first of all, these 2's would cancel. And you would have 1 over, what would that be? X to the 1/2 power. I should probably write that out, because this is the same thing as 1 over x divided by 1 over x to the 1/2. And to divide by a fraction is multiplied by the reciprocal. And then you could subtract those exponents. So as we get infinitely large in the denominator, that's our clue that we get closer and closer to 0. You're splitting $1 amongst a infinitely large, if you want to think of it that way. So as we move on to the next one, we're plugging in 1/2. So in the denominator, we for sure have e to the 1/2 minus e to the 1/2, which would give me 0. So my clue is that we're going to get 0 in the numerator. And think about where pi over 2 is up here. That is 0. So it is 1/2 times 0, which is 0. So we can say L'Hopital's applies. We have 0 over 0. And now we can take the derivative of top and bottom. Limit as x approaches 1/2. Now maybe you start with the denominator, because the derivative of e to the x is e to the x. Now remember, this is a constant. I don't know what e to the 1/2 power is, but I know it's always the same number. In the numerator, you have the chain and the product rule, where the derivative of x is 1, cosine of pi x. You leave that alone, plus now you leave the cosine alone, and the derivative of I said that wrong. You leave x alone. The derivative of cosine is negative sine of pi x times the derivative of pi x, which would be times pi. So as we look at this, the nice thing is we already did the preliminary work on this. That cosine of pi times 1/2 is 0. So then doing the next one, I believe we will get an answer, negative 1/2 sine of pi over 2 is 1 times pi all over e to the 1/2 power. So just to somewhat clean that up, you might rewrite it as negative pi over 2 square root of e. Kind of second guessing my answer here, so I'm going to check with the answer key. Yeah, that's exactly what he had. Written a little bit nicer. And by all means, if you feel like pausing the video and writing down what he has, I am not offended. Anyway. Progressing through a couple more problems. I do expect you to know that e to the 0 power equals 1. So as you work through that, you have 1 minus 1 on top, which is 0. If you look in the bottom again, e to the 0 power is 1. And I do expect you to know that that's natural log of 1. I do expect you to know that natural log of 1 is always 0. These are things we did learn in pre-calc, so we got to stick with it. So L'Hopital's applies. We have 0 over 0. Maybe it'd be a good idea to write out after doing that arithmetic. 0 over 0 implies L'Hopital's, a little symbol for implication. So then we can do the derivative of top and bottom. Limit as x approaches 0 of negative e to the x over, remember that derivative is 1 over 2 minus e to the x times the derivative of the inside, which looks like it's just negative e to the x, which is kind of nice because that would cancel out these things. So this would be equal to the limit as x approaches 0. Remember, to divide by a fraction is multiply by their reciprocal. And e to the 0 power is 1. 2 minus 1 should be 1. It was way too easy for such a complicated start to a problem. But the answer key matches. So I'm going to encourage you to pause the video and try the next one. I really do not like this guy's work because at no point does he show 0 over 0 or the work that leads to it. Because on the AP test, they expect to see that you write 0 over 0 or infinity over infinity, unless it's a multiple choice question. So here is your last problem for you to work out, make sure you understand, and you should be ready for the homework. Let me double check. So you might want to hit pause. I'm going to go back to my notes. Yep, your homework's on the next page.